Imagine boarding an aircraft in New York, fastening your seatbelt, feeling a gentle push back into your seat. And before you've even finished your drink, you're landing in London. No overnight flight, no jet lag, no fossil fuel exhaust trailing behind you. Just pure speed, powered by hydrogen, cutting through the upper edge of Earth's atmosphere at more than 5 times the speed of sound. This is not science fiction. This is not a futuristic concept sketch meant to impress investors. This is the direction aviation is moving toward right now. The world's first hydrogen-powered hypersonic jet is emerging as one of the most disruptive technologies ever conceived, and it has the potential to change how humanity travels, how nations project power, and how the planet deals with climate pressure. To understand why this aircraft is such a game-changer, we need to rethink what flight actually means. For more than half a century, commercial aviation has barely changed in principle. Modern jets are faster, safer, and more efficient than their predecessors, but they still operate in the same speed range. Most airliners cruise just below the speed of sound. Even the legendary Concorde, which once represented the peak of aviation ambition, only reached about twice the speed of sound. Hypersonic flight exists in an entirely different realm. Hypersonic speed begins at Mach 5. That is 5 times the speed of sound, over 6,000 kilometers per hour. At those velocities, air no longer behaves like the gentle fluid pilots are used to. It compresses violently. Temperatures skyrocket. The surface of an aircraft can glow red-hot from friction alone. The physics change so dramatically that many of the assumptions of conventional aviation simply break down. For decades, hypersonic flight was reserved for experimental vehicles, missiles, and short-duration military tests. These systems were often rocket-powered, expensive, and incapable of sustained, controlled flight. They were not reusable in any practical sense. They were not designed to carry passengers or cargo across the world. Hydrogen is what changes everything. Hydrogen is the lightest element in the universe, yet it carries extraordinary energy. By weight, it contains nearly 3 times more energy than traditional jet fuel. That single fact makes it incredibly attractive for high-speed aviation, where every kilogram matters. Less weight means higher speeds, longer range, and better performance in extreme conditions. But hydrogen's importance goes far beyond raw energy density. It burns incredibly fast, which is essential for hypersonic propulsion. At Mach 5 and beyond, air passes through an engine in milliseconds. Conventional fuels simply cannot combust efficiently in that time window. Hydrogen can. And then there's the environmental impact. When hydrogen burns, it produces water vapor. No carbon dioxide, no soot, no sulfur emissions. In a world under intense pressure to decarbonize transportation, hydrogen offers a path to extreme speed without the climate cost that would otherwise make hypersonic travel politically and socially impossible. At the heart of the hydrogen hypersonic jet lies one of the most radical engines ever developed, the Scramjet. Unlike a traditional jet engine, a Scramjet has no moving parts, no fan blades, no turbines, no compressors. Instead, it relies entirely on the forward speed of the aircraft itself. As the jet flies faster and faster, air is forced into the engine at enormous pressure. Hydrogen is injected directly into this supersonic airflow and ignites almost instantly. The explosion pushes the aircraft forward even faster, compressing more air, sustaining combustion in a self-reinforcing cycle. This concept sounds elegant, but it is brutally difficult to execute. For years, scramjets only worked for a few seconds at a time. Keeping combustion stable while air is moving faster than sound is one of the hardest problems in aerospace engineering. Temperatures soar, materials weaken, tiny instabilities can shut the engine down instantly. Hydrogen makes sustained scramjet operation possible in a way no other fuel can. Its fast ignition speed, clean burn and cooling properties allow engineers to stretch hypersonic flight from seconds into minutes and eventually into hours. That brings us to the aircraft itself. Across the world, multiple teams are racing toward the same goal: a reusable, hydrogen-powered hypersonic jet capable of taking off from a runway, accelerating to Mach 5 and beyond, cruising at near space altitudes, and landing like a conventional airplane. Europe has unveiled ambitious hydrogen aviation concepts through major aerospace players. The United States is quietly combining decades of military hypersonic research with new clean energy initiatives. China has invested heavily in advanced propulsion and high-temperature materials, with several programs remaining classified. Alongside governments, private aerospace startups are pushing innovation at unprecedented speed, unburdened by legacy thinking. What makes this moment different from past hypersonic efforts is convergence. Climate urgency, geopolitical competition, and technological maturity are all aligning at once. One of the greatest challenges in hypersonic flight is heat. At Mach 5, friction with the atmosphere can raise surface temperatures beyond 1,000 degrees Celsius. Aluminum melts, steel weakens, even advanced alloys struggle. The solution lies in a combination of exotic materials and clever engineering. Advanced ceramic composites can withstand extreme temperatures while remaining lightweight and strong. These materials are closer to those used in spacecraft than traditional airplanes. But the most ingenious solution uses hydrogen itself. Before the fuel ever reaches the engine, it is circulated through channels in the aircraft's skin. As hydrogen flows through these channels, it absorbs heat, cooling the structure from within. By the time it reaches the engine, the hydrogen is already warm and ready for combustion. The fuel becomes both an energy source and a thermal shield. This dual role is one of the reasons hydrogen is uniquely suited to hypersonic flight. The aircraft doesn't just fly on hydrogen. It survives because of it. If such a jet becomes operational, its impact will extend far beyond civilian travel. From a strategic perspective, hypersonic aircraft redefine distance. A vehicle capable of crossing continents in under 2 hours changes military logistics, emergency response, and global reach. Troops, supplies, or critical equipment could be moved faster than ever before. Surveillance and reconnaissance capabilities would expand dramatically. This is why hypersonic technology is often discussed in hushed tones by defense analysts. The ability to move at such speed without relying on rockets or missiles represents a shift in power that few nations want to openly discuss. Yet the most visible impact may come in commercial aviation. Long-haul flights are one of the most exhausting aspects of modern travel. 10 to 15 hours in a pressurized cabin, disrupted sleep cycles, jet lag that lingers for days. Hypersonic hydrogen jets promise to erase those experiences. A business traveler could attend a morning meeting in New York and be back home in Europe the same evening. Medical teams could reach disaster zones on the other side of the planet in under an hour. Global tourism would be reshaped, not by cheaper tickets, but by radically reduced time costs. Airports themselves would evolve. With travel times compressed, hub-and-spoke systems might give way to more direct global routes. Time zones would matter less. The psychological distance between continents would shrink dramatically. Of course, enormous challenges remain. Hydrogen must be stored at extremely low temperatures or high pressures, requiring new tank designs and safety protocols. Global hydrogen infrastructure is still in its infancy. Sonic booms generated by hypersonic flight pose regulatory and environmental concerns, especially over populated areas. Certification processes for entirely new propulsion systems will take years. Cost is another major factor. Early hypersonic hydrogen jets will be expensive, likely reserved for government use, research, and ultra-premium commercial travel. But history shows that aviation technologies tend to follow a familiar pattern: prohibitively expensive at first, then steadily more accessible as scale and efficiency improve. The jet engine itself was once considered impractical for commercial use. So was spaceflight. So were electric vehicles. What makes this moment truly different is timing. Humanity is under pressure to reinvent transportation. Climate targets are tightening. Public tolerance for carbon-heavy industries is shrinking. At the same time, computational power, materials science, and propulsion research have reached levels that previous generations could only dream of. Hypersonic hydrogen flight sits at the intersection of all these forces. The question is no longer whether this technology will exist. The real question is who will master it first, how it will be deployed, and whether it will be used to connect the world more closely or deepen global divides. Because once humans unlock routine hypersonic travel, powered by clean energy, there is no going back. The map of the world doesn't change physically, but mentally, everything becomes closer. Distance loses its meaning. Time becomes the new currency. And when that happens, aviation will never be the same again. As revolutionary as the idea sounds, the hydrogen hypersonic jet is not appearing out of thin air. It is the result of decades of quiet experimentation, failed prototypes, classified tests, and scientific persistence. Many of the technologies behind it were born in military laboratories during the Cold War, where speed was synonymous with survival. Back then, the goal was not sustainability or commercial travel. It was dominance. What has changed is how those technologies are now being repurposed for an entirely new era. For most of aviation history, speed came at a cost. Faster aircraft meant louder engines, higher fuel consumption, and greater environmental damage. The Concorde was the perfect example. It was breathtakingly fast, but economically fragile and environmentally controversial. Sonic booms restricted its routes. Fuel costs limited profitability. Public pressure eventually grounded it. That experience left a lasting scar on supersonic and hypersonic ambitions. Hydrogen rewrites that equation. Unlike conventional fuels, hydrogen allows engineers to chase extreme speed while simultaneously addressing emissions. That dual promise is why governments that once shut down high-speed aviation programs are now reopening them under a new banner: clean hypersonic flight. Another critical factor is altitude. Hypersonic jets do not fly where ordinary airplanes operate. They skim the edge of the atmosphere, at altitudes where air is thin and drag is reduced. At those heights, the curvature of Earth becomes visible. The sky darkens. The aircraft experiences conditions closer to spaceflight than traditional aviation. This altitude profile offers additional advantages. Weather disturbances are minimal. Turbulence is reduced. The aircraft spends less time fighting dense air, improving efficiency. In many ways, hypersonic jets behave like spacecraft that never fully leave the planet. But that also introduces new engineering challenges. At near-space altitudes, traditional aerodynamic control surfaces lose effectiveness. Engineers must design advanced flight control systems that can operate across wildly different atmospheric conditions. During takeoff and landing, the jet behaves like a plane. During cruise, it behaves like something else entirely. Artificial intelligence and advanced automation are becoming essential. Human pilots alone cannot react fast enough at Mach 5. Flight computers must constantly adjust airflow, fuel injection, thermal loads, and stability. In many proposed designs, the pilot becomes more of a systems manager than a traditional stick-and-rudder operator. This shift mirrors what happened in spaceflight and modern fighter jets. As speed and complexity increase, autonomy becomes unavoidable. Then there is the question of sound. At hypersonic speeds, shock waves are inevitable. Sonic booms are not just loud noises, they are pressure waves that can rattle buildings and disturb communities. Regulators around the world have long restricted supersonic flight over land for this reason. Hypersonic flight amplifies the challenge. Engineers are exploring new airframe shapes designed to spread shock waves over longer distances, reducing their intensity at ground level. Flying at extremely high altitudes also helps dissipate sound before it reaches the surface. While the sonic boom problem is not fully solved, progress is being made, and it is no longer seen as an insurmountable barrier. Infrastructure is another piece of the puzzle. Hydrogen-powered hypersonic jets require an entirely new ecosystem. Airports must be equipped to store and handle liquid hydrogen safely. Maintenance crews need specialized training. Emergency response protocols must be rewritten. None of this happens overnight. However, the global push toward hydrogen for energy storage, shipping, and ground transportation means aviation will not be building this infrastructure alone. Ports, power plants, and industrial hubs are already investing billions into hydrogen supply chains. Aviation can piggyback on that momentum. Economics will determine how fast this transition happens. Initially, hydrogen hypersonic jets will not replace conventional airliners. They will complement them. Early use cases are likely to include government missions, scientific research, urgent cargo delivery, and premium passenger routes where time savings justify higher costs. As production scales and technology matures, costs will fall. That pattern is consistent across every major aviation breakthrough. The first jetliners were rare and expensive. Today, they are ubiquitous. There is also a psychological element to consider. Human perception of distance has shaped culture, economics, and geopolitics for centuries. Oceans once took months to cross, then weeks, then hours. Each reduction in travel time reshaped how societies interacted. Hypersonic hydrogen jets could compress the world in ways we have never experienced. When any two major cities are separated by less than 2 hours, global collaboration accelerates. Business decisions speed up. Cultural exchange intensifies. Borders feel less distant, even if they remain politically significant. This compression of time could have profound consequences. It may benefit innovation and cooperation, but it could also intensify competition. When distance is no longer a barrier, economic disparities and geopolitical tensions can sharpen. That duality is why this technology inspires both optimism and concern. Supporters see a cleaner, faster, more connected world. Critics worry about militarization, inequality, and environmental side effects at high altitudes. Water vapor released in the upper atmosphere behaves differently than emissions near the ground. Scientists are still studying its long-term climate impact. These debates are not reasons to stop progress, but they are reminders that transformative technologies must be guided carefully. One thing is certain: the nations and companies that lead in hydrogen hypersonic flight will shape the next century of aviation. Just as those who mastered jet engines dominated the skies in the 20th century, mastery of hypersonic hydrogen systems will define leadership in the 21st. This is why investment is accelerating quietly but aggressively. Prototypes are being tested. Wind tunnels are running around the clock. Supercomputers simulate airflow patterns that would have been impossible to calculate just a decade ago. We are watching the early stages of a revolution. In the coming years, announcements will become more frequent. Demonstration flights will last longer. Speeds will increase. What once sounded impossible will slowly become routine. The first successful hydrogen hypersonic jet will not look dramatic to the untrained eye. It will simply take off, disappear into the sky, and land somewhere far away far sooner than anyone expects. And when that happens, the question people will ask will not be how fast it flew or what fuel it used. They will ask why it took so long for aviation to change. Because once you experience a world where continents feel close, where time bends to technology, and where speed no longer demands environmental sacrifice, there is no appetite to return to the old way of flying. This is not just a new aircraft. It is a new chapter in humanity's relationship with distance, energy, and the sky. As this technology moves from concept to reality, it forces us to confront a deeper truth about human progress. Every major leap in transportation has done more than move people faster. It has reshaped economies, rewritten geopolitics, and redefined what is possible within a single human lifetime. The hydrogen hypersonic jet belongs to that rare category of inventions that don't simply improve the world as it is, but actively create a new one. Think about what speed really represents. Speed is freedom from delay, freedom from isolation, freedom from the invisible barriers created by time. For centuries, oceans protected nations, distance preserved cultures, slowness defined strategy. Hypersonic travel erodes all of that. When distance collapses, the world becomes more interconnected, but also more exposed. That is why this aircraft is more than an engineering achievement. It is a strategic asset, a climate statement, and a cultural turning point rolled into one. From a technological standpoint, the hydrogen hypersonic jet represents the convergence of multiple breakthroughs that matured at exactly the right moment. Advanced materials capable of surviving extreme heat, artificial intelligence systems that can manage flight at speeds humans cannot react to, hydrogen production methods becoming cleaner and more scalable, decades of hypersonic research finally reaching operational reliability. None of these developments alone would be enough. Together, they unlock something extraordinary. The jet itself is a symbol of efficiency under pressure. Every design choice is dictated by physics. Every curve exists for a reason. Every system serves multiple purposes. Fuel becomes coolant. Speed becomes compression. Air becomes both obstacle and engine. There is a kind of elegance in how ruthlessly optimized hypersonic design must be. That elegance reflects a broader shift in how humanity approaches innovation. We are no longer in an era where brute force solutions are acceptable. Burning more fuel, adding more power, or ignoring environmental consequences is no longer viable. The future belongs to technologies that do more with less, that turn constraints into advantages. Hydrogen hypersonic flight embodies that philosophy. Environmentally, it offers a rare narrative of hope. Aviation has long been criticized as incompatible with climate goals. Even incremental efficiency gains often felt insignificant compared to the scale of global emissions. Hydrogen changes the conversation. It does not solve every environmental challenge, but it opens a credible path toward high-speed, long-distance travel with drastically reduced carbon impact. That matters not just for regulators and policymakers, but for public perception. Technologies that fail to align with environmental values increasingly struggle for acceptance. Hydrogen hypersonic jets, if implemented responsibly, could redefine aviation as part of the solution rather than part of the problem. Culturally, the impact could be profound. When travel times shrink dramatically, the idea of far away begins to lose meaning. Families separated by continents could reunite more often. Global collaboration could accelerate. Education, science, and business could operate on truly planetary timescales. At the same time, this compression of distance will test global systems. Immigration policy, border security, trade regulation, and international law were built for a slower world. Hypersonic travel challenges assumptions embedded deep within those frameworks. Adapting to this new reality will require not just new aircraft, but new thinking. And then there is the human factor. For pilots, engineers, and passengers alike, hypersonic hydrogen jets will demand trust. Trust in automation, trust in new fuels, trust in systems operating at the edge of known physics. That trust will not be built overnight. It will be earned through testing, transparency, and time. The first passengers to board such an aircraft will not just be travelers. They will be participants in history. Just as the first jet passengers experienced a sense of awe mixed with uncertainty, so too will the pioneers of hypersonic flight. Eventually, though, wonder becomes routine. What once felt miraculous becomes normal. Children born into a world of hypersonic travel will grow up unable to imagine spending half a day crossing an ocean. Progress has a way of making its own past seem inefficient. Looking ahead, the hydrogen hypersonic jet is unlikely to be the final form of high-speed flight. It is a stepping stone. Lessons learned from these aircraft will inform spaceplanes, orbital logistics, and perhaps even point-to-point suborbital travel. Each breakthrough expands the design space for the next. In that sense, this jet is not an endpoint. It is a beginning of cleaner speed, a beginning of redefined distance, a beginning of aviation's next great era. The skies above us have always reflected who we are as a species. From fragile propellers to roaring jet engines, from experimental rockets to reusable spacecraft, flight has mirrored our ambitions and our fears. The hydrogen hypersonic jet reflects a world striving to move faster without destroying itself in the process. It asks a bold question. Can humanity push the limits of speed, power, and reach while also respecting the planet that makes flight possible? If the answer is yes, then this aircraft will be remembered not just as the world's first hydrogen hypersonic jet, but as the moment aviation chose a smarter future, a future where time bends, distance fades, and the sky once again becomes a place of possibility rather than limitation. And when that first hydrogen hypersonic jet slices through the upper atmosphere, silent to those below, leaving nothing behind but a trail of water vapor and a ripple in history, we will know that the game has truly changed. If you found this video insightful, make sure to like, subscribe, and share it with anyone who's fascinated by the future of aviation and breakthrough technology. Your support helps this channel bring you deeper stories about the innovations shaping tomorrow. Thanks for watching, and I'll see you in the next video.